In this segment, we ask whether we can build block ciphers from simpler primitives like pseudorandom generators. And we're going to show that the answer is yes. So to begin with, let's ask whether we can build pseudorandom functions as opposed to pseudorandom permutations from a pseudorandom generator. Okay? Can we build a PRF from a PRG? Our ultimate goal, though, is to build a block cipher, which is a PRP. And we'll get to that at the end. Okay, for now we build a PRF. So let's start with a PRG that doubles its input. Okay, so the seed for this PRG is an element in K, and the output is actually 2 elements in K. So here we have a schematic of this generator that basically takes as input a seed in K and outputs 2 elements in K as its output. And now what does it mean for this PRG to be secure? Recall, this means that essentially the output is indistinguishable from a random element inside of K squared. Now it turns out it's very easy to define basically what's called a 1-bit PRF from this PRG. So what's a 1-bit PRF? It's basically a PRF whose domain is only 1 bit. Okay, so it's a PRF that just takes 1 bit as input. Okay, and the way we'll do it is we'll say if the input bit x is 0, output the left output, and if the input bit x is 1, output the right output of the PRF. Okay, in symbols basically we have what we wrote here. Now it's straightforward to show that in fact if G is a secure PRG, then this 1-bit PRF is in fact a secure PRF. If you think about it for a second, this is really a tautology. It's really just stating the same thing twice. So I'll leave it for you to think about this briefly and see and convince yourself that in fact this theorem is true. The real question is whether we can build a PRF that actually has a domain that's bigger than just 1 bit. Ideally, we'd like the domain to be 128 bits, just say as AES has. So the question is, can we build a 128-bit PRF from a pseudorandom generator? Well, so let's see if we can make progress. So the first thing we're going to do is we're going to say, well, again, let's start with a PRG that doubles its input. Let's see if we can build a PRG that quadruples its input. Okay, so it goes from k to k to the 4th instead of k to k squared. Okay, so let's see how to do it. So here we start with our original PRG that just doubles its input. But now remember, the fact that this is a PRG means that the output of the PRG is indistinguishable from 2 random values in K. Well, if the output looks like 2 random values in K, we can simply apply the generator again to those 2 outputs. So let's say we apply the generator once to the left output and once to the right output. And we're going to call the output of that, this quadruple of elements, we're going to call that G1K. And I wrote down in symbols what this generator does, but you can see basically from this figure exactly how the generator works. Okay, so now that we have a generator from k to the 4th, we actually get a 2-bit PRF. Namely, what we'll do is we'll say, given 2 bits, 0, 0, 0, 1, 1, 0, or 1, 1, we'll simply output the appropriate block that's the output of G1K. Okay, so now we can basically have a PRF that takes 4 possible inputs as opposed to just 2 possible inputs as before. So the question you should be asking me is, why is this G1K secure? Why is it a secure PRG? That is, why is this quadruple of outputs indistinguishable from random? And so let's do a quick proof of this. We'll just do a simple proof by pictures. So here's our generator that we want to prove is secure. And what that means is we want to argue that this distribution is indistinguishable from a random 4-tuple in k to the 4th. Okay, so our goal is to prove that these 2 are indistinguishable. Well, let's do it one step at a time. We know that the generator is a secure generator. Therefore, in fact, the output of the first level is indistinguishable from random. In other words, if we replace the first level by truly random strings, these 2 are truly random picked in the key space, then no efficient adversary should be able to distinguish these 2 distributions. In fact, if you could distinguish these 2 distributions, it's easy to show that you would break the original PRG. Okay, but essentially you can see that the reason we can do this replacement, we can replace the output of G with truly random values, is exactly because of the definition of the PRG, which says that the output of the PRG is indistinguishable from random, so we might as well just put random there, and no efficient adversary can distinguish the resulting 2 distributions. Okay, so far so good. But now we can do the same thing again to the left-hand side. In other words, we can replace these 2 pseudo-random outputs by truly random outputs. And again, because the generator G is secure, no efficient adversary can tell the difference between these 2 distributions. Put differently, if an adversary can distinguish these two distributions, then we would also get an attack on the generator G. And now finally, we're going to do this one last time. We're going to replace this pseudo-random pair by a truly random pair, and then lo and behold, we get the actual distribution that we were shooting for. We will get a distribution that's really made of 4 independent blocks. And so now we've proved this transition, basically, that these two are indistinguishable, these two are indistinguishable, and these two are indistinguishable, and therefore these two are indistinguishable, which is what we wanted to prove. Okay, so this is kind of the high-level idea for the proof. It's not too difficult to make this rigorous, but I just wanted to show you kind of the intuition for how the proof works. Well, if we were able to extend the generator's output once, there's nothing preventing us from doing it again. So here's a generator G1 that outputs 4 elements in the key space. And remember, the output here is indistinguishable from a random 4 tuple. That's what we just proved. And so there's nothing preventing us from applying the generator again. So we'll take the generator, apply it to this random looking thing, and we should be able to get this random looking thing, this pair over here that's random looking. And we can do the same thing again and again and again. And now basically we've built a new generator that outputs elements in k to the 8th as opposed to k to the 4th. And again, the proof of security is pretty much the same as the one I just showed you. Essentially, you gradually change the outputs into truly random outputs. So we would change this to a truly random output, then this, then that, then this, then that, and so on and so forth. Until finally we get something that's truly random, and therefore the original two distributions we started with, G2K and truly random, are indistinguishable. Okay, so far so good. So now we have a generator that outputs elements in k to the 8th. Now if we do that, basically we get a 3-bit PRF. In other words, at 0, 0, 0, this PRF would output this block, and so on and so forth, until 1, 1, 1, it would output this block. Now the interesting thing is that in fact this PRF is easy to compute. So for example, suppose we wanted to compute the PRF at the point 1, 0, 1. Okay, it's a 3-bit PRF. So 1, 0, 1. How would we do that? Well, basically we would start from the original key K, and now we would apply the generator G, but we would only pay attention to the right output of G, because the first bit is 1. And then we will apply the generator again, but we would only pay attention to the left output of the generator, because the second bit is 0. And then we would apply the generator again and only pay attention to the right outputs, because the third bit is 1, and that would be the final output. Right? So you can see that that led us to 1, 0, 1, and in fact, because the entire generator is pseudorandom, we know in particular that this output here is pseudorandom. Okay, so this gives us a 3-bit PRF. Well, if it worked 3 times, there's no reason why it can't work n times. And so if we apply this transformation again and again, we arrive at what's called the GGM PRF. GGM stands for Goldreich, Goldwasser, and Micali. These are the inventors of this PRF. And the way it works is as follows. So we start off with a generator that just doubles its output. And now we're able to build a PRF that acts on a large domain, namely a domain of size 0, 1 to the n, where n could be as big as 128 or even more. So let's see. Suppose we're given an input in 0, 1 to the n. Let me show you how to evaluate the PRF. Well, by now you should actually have a good idea for how to do it. Essentially, we start from the original key, and then we apply the generator, and we take either the left or the right side, depending on the bit x0. And then we arrive at the next key, k1. And then we apply the generator again, and we take the left or the right side, depending on x1, and we arrive at the next key. And then we do this again and again, until finally we arrive at the output. So we've processed all n bits, and we arrive at the output of this function. And basically, we can prove security, again, pretty much along the same lines as we did before. And we can show that if G is a secure PRG, then in fact we get a secure PRF on 0, 1 to the n, on a very large domain. So that's fantastic. So now we have, essentially, we have a PRF that's provably secure, assuming the underlying generator is secure. And a generator is supposedly much easier to build than an actual PRF. And in fact, it works on blocks that could be very large, in particular 0, 1 to the 128, which is what we needed. So you might ask, well, why is this thing not being used in practice? And the reason is that it's actually fairly slow. So imagine we plug in as a generator, imagine we plug in the salsa generator. So now to evaluate this PRF at 128-bit inputs, we would basically have to run the salsa generator 128 times, 1 time per bit of the input. but then we would get a PRF that's 128 times slower than the original salsa, and that's much, much, much slower than AES. AES is a heuristic PRF, but nevertheless, it's much faster than what we just got here. And so even though this is a very elegant construction, it's not used in practice to build pseudo-random functions, although in a week we will be using this type of construction to build a message integrity mechanism. So the last step is basically, now that we have built a PRF, the question is whether we can actually build a block cipher. In other words, can we actually build a secure PRP from a secure PRG? Everything we've done so far is not reversible. Again, if you look at this construction here, we can't decrypt. Basically, given the final output, it's not possible to go back, or at least we don't know how to go back to the original input. So now the question of interest is, can we actually solve the problem we wanted to solve initially? Namely, can we actually build a block cipher from a secure PRG? So I'll let you think about this for a second and mark the answer. So of course, I hope everybody said the answer is yes, and you already have all the ingredients to do it. In particular, you already know how to build a PRF from a pseudorandom generator. And we said that once we have a PRF, we can plug it into the Luby-Rokov construction, which, if you remember, was just a 3-round Feistel. So we said that if you plug a secure PRF into a 3-round Feistel, you get a secure PRP. So combining these two together basically gives us a secure PRP from a pseudorandom generator. And this is provably secure as long as the underlying generator is secure. So it's a beautiful result, but unfortunately, again, it's not used in practice because it's considerably slower than heuristic constructions like AES. Okay, so this completes our module on constructing pseudorandom permutations and pseudorandom functions. And then in the next module, we're going to talk about how to use these things to do proper encryption.